Welcome back. In this brief lecture, we will introduce some aspects of battery management system, often referred by its acronym BMS. BMS is very critical for the safety of the battery, and what BMS does is it mainly monitors the input and output current. It uses this information, the voltage information, and the temperature of the battery to estimate the state of charge and state of health of the battery to control the charging and discharging current. We've already talked about state of charge, how that is connected to resistance of the battery and so on. So all these measurements go into estimating this and to control the charging and discharging current. There are a lot of hardware and software that goes into the BMS, and the aim of BMS is to balance the cell. So what we mean by cell balancing is that when many cells are in series, you want all the cells to have the same current. By electrical design, they are in series, therefore same current passes through all the cells. So you want all these cells to be in having the same state of charge. That may not happen. So there is a lack of cell balance. For example, one way how you can imagine cell imbalance to occur is the following. Supposing you start the battery with the state of charge being 80%, and it is discharged to 30% state of charge. So there is a 50% decrease in state of charge. When you try to charge the battery back, even though you supply the amount of charge equivalent to the amount of charge that was utilized during discharge, all this charge does not get back the battery to 80%. So from 30%, even though you've supplied sufficient charge, it only goes to some 74% state of charge. So there is some efficiency loss. Okay, so there is some inefficiency in charging. So it gets the state of charge to only 74. Again, when you discharge the battery from 74, you go to 24. Again, there's a 50% decrease in state of charge. When you recharge the battery, even though you apply the same amount of charge, you do not get back to 74 or 80. You get back only to some lesser state of charge, 68. So 68 minus 50 is 18. You go to a lesser value and so on. So with every cycle, the state of charge keeps on decreasing. So when you discharge the battery, the state of charge keeps on decreasing, right? So from 30, 24, it has come down to 5. So what is the outcome, battery outcome you desire? You want to get out this much amount of charge. While doing so, because of some inefficiency in charging, with every cycle, the state of charge decreases. So if one of the cell behaves in this manner, the other cells do not behave in this manner. For example, other cell, while we discharge to 30%, when you recharge, you may get back to 80%. Okay. So, but in one of the cell, if it behaves in this manner, there is cell imbalance. There are many reasons for cell imbalance. Even a slight difference in self-discharge might also give rise to a different state of charge in a battery. So when they're all in series, this creates a lot of issues. So this is what we mean by cell imbalance amongst the cells that are in series. So there are different ways of addressing charge um, imbalance, cell imbalance. So they can broadly be classified under two categories. There are cell chemistries that can tolerate overcharge. We have already discussed what are some of such cell chemistries. For example, lead acid battery, nickel battery can tolerate overcharge. They are not too sensitive to overcharging. So they can be brought to same state of charge by overcharging. Supposing there is this gradual decrease in state of charge, right? So by overcharging, you can get them to the same state of charge, okay, the desired state of charge. But this is not very efficient, right? Because you are overcharging the battery. But in some battery chemistries, for example, lithium ion battery, they do not, they're very sensitive to overcharging because overcharging causes permanent changes, detrimental changes to lithium ion battery. So you want to avoid this overcharging, and this strategy is not applicable. So in the case of lithium ion battery, a strict monitoring of state of charge is ideal to prevent cell imbalance. So there are, again, you can classify the cell balancing strategies into two categories again. One is called the active balancing, another is passive balancing. So all these things depend upon hardware and software design that goes into the BMS. If you have string of batteries or string of cells rather, when cell are in series within a battery, although same current passes through all the cells that are in series, the voltage of each of the battery may differ. So in passive balancing, what you try to do is that when the current that is passed, that is amongst the cells that are in series, you bypass some part of the current through a shunt. You might have heard this jargon, shunt, in your electrical engineering class. So what does shunt mean? You bypass some current. Okay, so supposing these are cells that are in series, when a cell has higher state of charge, when current passes through such a cell, some part of that current is bypassed through a shunt. So this is called passive balancing. This is not the most efficient way of providing balance to cells in series, but this is the design of passive balancing is easier compared to what is called active balancing. In active balancing, energy from a cell that has high state of charge is supplied to another cell that has low state of charge. So this is more energy efficient, but the design of active balancing is more complicated. The hardware and software that goes into active balancing is more complicated. So these are the typical trade-off in engineering. Okay, so when something has to be done efficiently, you have to increase the complexity that goes into the design of an efficient system. In the next lecture, we will briefly touch upon this topic called state of charge. Thank you.